Hello grade 12s and welcome to my page or to my channel once again. On today's video we will be covering a chapter under physical sciences. It's a new chapter. It's Doppler effect. So we are deep, not really deep, but we've just gotten into term 2, and I believe that you guys have already settled, and I know it is at this time that you're starting to feel like you are really in matric, because we are now introducing some new chapters, the grade 12 chapters. So please grab a seat, grab a pen and a book, and let us go through Doppler effect. Starting with the definition of Doppler effect. Doppler effect is the apparent change in frequency of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay, so this is the definition. You need to know it word to word, and as you can see, some words that are underlined on the definition, just to show you that these are the key words that must be part of your definition, and you need, I still repeat, know it word by word. So we are saying it is the apparent change in frequency of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. So in simple terms, when we talk about Doppler effect, we are saying, say for an example, you are standing at your gate at your house, and as you are standing at your house, your friend is approaching you holding a bazooka speaker, those mobile speakers, the loud ones, holding a bazooka speaker, and your friend is walking towards you, playing some great music, playing the beat through the speaker. And what happens now as your friend is approaching? What do you observe about the sound? What is happening? So yes, I know you can agree with me that when your friend was still a further away from you, the sound was a bit low, but as they are moving closer and closer and closer, you are starting to feel like the sound is getting higher and higher and higher and higher. Okay, and then now they get to you. Your friend chats with you for a moment, and then he's like, okay, I'm not here to stay, I'm rushing off to somewhere. So now they pass you and start to move now away from you. And now when your friend is now moving away from you, still holding the speaker and still playing the beat, what do you notice about the sound now? So now the sound is getting lower and lower and lower. You are even getting angry that, man, you are moving away with the music and I was enjoying the beat. So it means when the sound source is coming towards you, what you hear is higher. You are hearing a high pitch, or we are saying the sound, you are hearing an increased frequency of the sound. But when the person or when the sound source is moving away from you, you are hearing a lower and lower and lower pitch, meaning the frequency is decreasing as you move with as the sound source moves away from you. Okay, so that is Doppler effect in simple terms. And then now, because when we explain Doppler effect, we bring in frequency, we bring in velocity. So there's frequency and there's also velocity. So the frequency now we relate it to pitch. Guys, pitch, it's just the highness of something, if it's sound, how high is the sound or how low is the sound. So pitch is the highness or the lowness, in this case, of the sound that is being emitted by the source. And then the velocity, this refers to the velocity of the sound, still the velocity of the sound, or the speed. Let us rather use speed because we use it as a vector. So V represents the speed of the sound, and this we had said it's the frequency, which can also be the pitch. And then now that there's a change, because there's velocity, it means there's movement, and there's also distance, between you and the sound source. This now makes us bring in the third parameter, which is now our wavelength. So now the wavelength, it just tells us how far is the sound source from the listener, or what is happening between the distance between the sound source and the listener. Is it getting smaller or is it getting bigger? Okay, so we do have a formula that puts in these three parameters together, and the formula is the velocity, or the speed rather, of sound. It's equals to the frequency of the sound times the wavelength. Okay, this is the formula that you can use to convert between frequency and wavelength, because we say the velocity of sound in air is constant. Okay, and then there is a relationship between this frequency and the wavelength. Let us make frequency the subject of the formula. It means frequency will be equals to the velocity of sound divided by the wavelength. So the relationship now states that frequency is inversely proportional to the wavelength, meaning the higher the frequency, the lower the wavelength, or the lower the frequency, the higher the wavelength. So they are inversely proportional. So, or we can explain it in terms of wavelength. If we now say we put the formula wavelength, it's equals to velocity over frequency. We are making wavelength the subject of the formula. We are saying now wavelength is inversely proportional to the frequency, meaning the longer the wavelength, the smaller the frequency, and the smaller or the shorter the wavelength, then that would mean that we have a higher frequency. So I'm going to take this relationship, come back here, and explain now what changes between the sound source and the listener, you and your friend. What changes led to you hearing a higher pitch when your friend was approaching you, and now a lower pitch when your friend was now moving away from you. So let us look at the point where the friend is now moving towards you. Because they're getting closer and closer and closer to you, it means the wavelength is shorter. So I'm just going to use lines that are closely packed together to represent wavelength. So in this case, we are saying the wavelength is shorter, meaning the frequency has to be higher. And this is the reason when the source of sound is moving towards you, you hear an even increased highness or increased pitch of the sound. This means frequency is increasing. But now, as your friend is moving away, rushing off to where they were heading to, now the wavelength is starting to get longer and longer. So in this case, it means our wavelength is now longer, meaning the frequency is going to be shorter. If frequency is shorter, it means pitch, the highness or the lowness of the sound is decreasing. So it means now you're starting to hear a lower and lower and lower pitch of the sound from the speaker. So this is how we can explain the change in what you hear from when you are being approached by the source or when the source is moving away from you. And if you think about it now, because we now are going to introduce two other parameters, not really two. Under frequency, we do have the frequency of the listener, and the frequency of the source. So the frequency of the listener is what you hear from the sound source. The frequency of the source is what the sound source is emitting. the frequency that the sound source is emitting. And then I will go on to add here on our diagram. When your friend is approaching you with the speaker, the frequency that you hear is greater than the frequency that the source emits. And when we are coming to when your friend leaves you or moves away from you, the frequency that you hear is now less than the frequency that the source emits. Okay, I want you to grab this little diagram here, because we will apply it when we do calculations on Doppler effect and also when we answer theory questions. Okay, so I will leave it at this point now, and I'm going to introduce now a new equation which we call the Doppler effect equation. So that is F at L, frequency of the listener. Remember guys, I did introduce frequency of the listener and frequency of the source up there. So the Doppler effect equation says the frequency of the listener is equals to the V. This V represents the velocity of the sound, or the speed. I don't know why do I keep on saying velocity, because it's a scalar. Now we use speed. The speed of the listener plus or minus the speed of the sound plus or minus the speed of the listener divided by the speed of the sound again plus or minus the speed of the sound source, all multiplied by the frequency of the source. Okay, this is the equation that we will use when we do calculations. There is one thing, however, that is going to change when we use this equation, and that is going to be the middle part there, plus or minus, plus or minus. So you have to choose which one is plus or which one is minus when you do the calculations. I'm going to now focus on the method that you can use to choose on whether you have to put a plus or a minus. So let us think about just a general fraction. We know that with the fraction, let's say f for fraction, not for frequency, f for fraction, the fraction it's equals to it has a numerator and it also has a denominator. From this fraction we can go on to say the fraction is directly proportional to the numerator, and the fraction is inversely proportional to the denominator. So this would mean that when the fraction increases, meaning whatever is on this side of the fraction, if it increases, this part is also going to increase. So an increase in that will cause an increase in the numerator, and a decrease in the fraction will cause a decrease in the numerator. However, with the distance it's going to be slightly not the distance. However, with the denominator it's going to be slightly different. When the fraction increases, meaning when this part increases, I'm just going to use a different colored pen. When this part increases, this one is going to decrease, and also when it now decreases, that is going to increase. So they work, they have an inverse relationship. I want you to grab the fraction part for now, because I'm going to show you how we are going to apply it on the Doppler effect equation. So I'm going to introduce some few cases, because in Doppler effect, guys, so far I've only mentioned that the sound source is moving. However, that is not always the case. In some cases, the listener will be the one that is moving while the sound source is stationary. So I'm going to show you how you can rearrange that formula or set up that Doppler effect formula under these conditions. Okay, I hope you're still with me, guys. Please make sure that you understand this part before we can get onto the next part. So case one, or let me not say case sounds heavy. Let us say, okay, number one, let us say now the listener is moving. listen. What is the spelling for listener? Listener is moving and source is stationary. Source is stationary. Okay, I think I don't have enough space there. Listener is moving, and it means also the source is stationary. And we know, guys, when something is stationary, it means it has what? A velocity of 0 meters per second. Okay, so now the listener is moving and the source is stationary. But 1.1, we are saying the listener is moving towards the source. So I'm just going to write towards. Listener is moving towards the source. Okay, I hope you're still with me. The listener is the one that is moving towards the source. I'm going to rewrite the Doppler effect formula. FL is equals to V plus or minus VL over V plus or minus Vs times Fs. Okay, so guys, let me go back to the Doppler effect. F at L is the frequency of the listener. The two velocities there, these are the speed. The two V's there represents the speed of sound. It's usually a constant. They do give you that. VL and Vs. VL is the speed of the listener and Vs is the speed of the sound source, and then Fs represents the frequency of the source. Okay, so that is what the equation tells us. So now we are saying the listener is moving towards the source. So it means we had said, guys, this case the source is stationary, meaning Vs is going to be 0. I'm going to now rewrite the equation with Vs being 0. FL is V plus or minus VL over just V. Over just V, because our velocity of source, our source is not moving. Our sound source is not moving. It has a velocity of 0. And then now let us look at the listener moving towards the source. So if the listener is moving towards the source, what can I use as the source? Let us say still the bazooka speaker. I love bazooka speakers. Yeah, it's playing some music. The listener is moving towards the source. Guys, remember, when a listener is moving towards the source, it would mean that the wavelength is going to be what? It's going to be very shorter. So our wavelength is going to be shorter and our frequency is going to be higher. So this frequency is the frequency of what? Of the listener. So FL is higher, meaning FL. So as the listener is moving towards the source, they're starting to hear an increase in the frequency or the pitch of the sound, meaning frequency of listener is increasing. If frequency of listener is increasing, this would mean that we expect the upper part there to increase, to be bigger, and the lower part to what? To decrease, to be smaller. And in order to have the upper part to be bigger than the lower part, it means the upper part must be positive. So this would mean that our FL is going to be V plus VL over V. Okay, so in order for F at L, no, not F at L, in order for FL to be if FL is increasing, the numerator is also increasing, the denominator is decreasing. It means the numerator will be greater than denominator. And in order for it to be greater, think about it, guys, we have to add there. We can't subtract, we have to add. So we are putting a plus there. This is when the listener is moving towards the source. And then 1.2, the listener is moving away from the source. So it means now the listener is still there, and the source, our bazooka, is right there, and the listener now is moving in that direction away from the source, meaning the wavelength is longer. So now we have our wavelength increasing and our frequency decreasing, our frequency of the listener. So it means the listener is starting to hear a decreased pitch of the sound. And now it means if we now rewrite the Doppler effect equation over V, we are saying that is decreasing. We expect that part to be smaller and that part to be bigger, meaning we want a smaller numerator and a bigger denominator. How can we get that? We need to subtract. We are going to write it as FL is equals to V minus VL over V. I hope we are happy with the case where the listener is the one that's moving. Okay, so I'm going to now jump into the second case where the source is the one that is moving. So in this case now we are saying source is moving, sound source, remember source is the sound source, and the listener is stationary, meaning the velocity of the listener, it's going to be 0. Okay, let us start with the first case, 2.1. The source is moving towards the listener. We are writing now the entire what do we call it, the Doppler effect equation, and we are saying now under these cases, because listener is stationary, that part is the one that is going to be 0. So it means we are going to take it out. That part over there is 0. So we just have FL, it's equals to V over V plus or minus VS times FS. And then if the source, so now I'm gonna put our friend there who was holding the speaker, and also you standing there, and my friend was moving towards the speaker. No, and my friend was moving towards the listener, or towards you as a listener. It means still we expect the wavelength to get smaller. If the wavelength gets smaller, it means the wavelength is decreasing, frequency is increasing. And if the wavelength is decreasing and frequency is increasing, if we rewrite that formula, we say FL is, now we have V there over V plus or minus VS times FL. If the frequency of the listener is increasing, this part over there is increasing, we expect that part to decrease and that one to increase. How can we get this? It means we expect the numerator to be bigger, the denominator to be smaller. So if we want to get the numerator to be bigger, the denominator to be smaller, it means we need to subtract on the denominator so that we have a smaller number. So we are rewriting the equation, the formula now as V over V minus VS times FS. Okay, I need to correct the formula there. It's FS, guys, my bad. So it is that simple, guys. You just check. You want the numerator to be big, the denominator to be small. It means the denominator must subtract so that it becomes smaller. And then case number 2.2, now the source is moving away. Okay, remember, guys, I was using the symbols, our S is moving away from the listener. S is moving away from L. So this guy now, or this friend of us now, is facing the other side. It's going in that direction, and you are just standing there and wondering, why is this person leaving me with this great music? And the wavelength is great. it's increasing now because the wavelength is increasing because the distance between you and the person is getting longer. So it means wavelength is increasing, and when the wavelength is increasing, it means the frequency is going to decrease. You're starting to hear an even lower and lower and lower pitch. And if we do write our equation, V over V plus or minus Vs times Fs, the frequency is now decreasing, my friend. And if the frequency is decreasing, that is going to increase, and that is going to sorry guys, that is going to decrease, and that is going to increase, because it's directly proportional to the numerator and inversely proportional to the denominator. So it means we want the numerator to be smaller, the denominator to be big. If something must be big, we must add, right? So it means I'm going to rewrite the formula now as FL is equals to V over V plus Vs times Fs. Okay, I hope guys you have gotten this, because this is going to help you when you decide on the plus or minus of this formula. Just remember, you just need to first write down the full formula and then check which one is stationary. Oh, after finding out that source is stationary or listener is stationary, you get rid of that velocity because it's a 0. Then now you decide who is moving away, who is moving towards. Do we want our numerator to be big? Do we want our denominator to be big? So if we want the numerator to be big, you plus. If you want the denominator to be big, you plus. If you want it to be small, you subtract. Okay, I hope you guys have gotten this. I think we are ready to jump onto our first example. I'm just gonna just still use you and your friend and that bazooka speaker of ours that we love, and it plays some nice beats. So remember when your friend at the beginning of the lesson, when your friend was approaching you and your friend was playing some great music, so he's there now still with the bazooka or the mobile speaker and playing some great music, and you as the listener, you are standing by your gate just staring at him and waiting for him to get to you. The velocity of sound, so here we're just doing like an example of a calculation. The velocity of sound, or the speed of sound, let us say it is 340 meters per second, and your friend is moving towards you. He's walking towards you. Your friend walking towards you, he's walking with the velocity of 10 meters per second, the speed of 10 meters per second, and the bazooka is emitting the frequency that is the frequency of, let us say, 820 hertz. So this is the frequency of the source, the frequency that your source, your friend's speaker emits. It is 820 hertz. Okay, and then the first question, we want to calculate your frequency, the frequency that you hear. We want to calculate FL. Okay, so remember, the first thing, you write the entire formula, V plus or minus VL over V plus or minus Vs times Fs. Who is moving? So just to add also, you as the listener, you are just standing at your gate, remember, and waiting for your friend to get to you with the beat. So you have a velocity of 0, meaning your velocity VL is going to be 0. Rewriting the formula, we have V, just a single V there, it's equals to V over V plus or minus Vs times Fs. Okay, so what is happening now? Your friend is moving towards you, meaning wavelength is what? Is wavelength increasing or decreasing? Our wavelength is decreasing. And what about our frequency? Our frequency is increasing, meaning the frequency that you hear the sound with, it's increasing, meaning we are increasing FL. If we increase FL, it means V is also increasing and the denominator is decreasing. We will expect V, the numerator, to be bigger than the denominator. And if we, meaning we want the numerator to be bigger, denominator to be smaller, it means you are going to have FL, it's equals to V over, to make this smaller, we subtract. And then now we can now put in our numbers. We got our velocity of sound, or the speed of sound, to be 340 over 340 minus the velocity of the source, or the speed of the source is 10, and then the velocity of the source, we had said it's 820 hertz. That is FL. And then if we plug the whole thing on a calculator, we have 340 divided by 340 minus 10. That gives me and then we multiply that with 820, and the frequency of the listener is 844,85 hertz, provided that they said we must give answer in 2 decimal places. So remember guys, at the beginning when we were looking at your friend approaching you, I had mentioned that if the source is approaching the listener, the frequency that the listener hears, it's greater the frequency that the source emits. And that is evident. The source emitted 820 hertz and you as a listener had 844.85 hertz. So this is also another way to make sure that you are on the right track. You should, when you do the calculation, you should already know what is expected. Are you expecting something bigger than what you have or smaller than what you have? Okay, so that is the first example. And then now let us say the source is now moving away from you. Your friend got to you and they were rushing off to somewhere, as I had mentioned earlier. So your friend now has passed you and he's now moving, heading towards I don't know, their next stop, or maybe to their destination, wherever they are going. So still holding the bazooka and still playing the beat, but now he's moving away, or she is moving away. The frequency, it hasn't changed. The frequency of the source, the speaker is still emitting 820 hertz. Nothing has changed. Your friend is still moving at the same velocity and you are still stationary, just worried that your friend is moving away with the beat, and we need to find the frequency of the listener. Okay, remember, first thing first, we need to check what is happening to our wavelength. Is it increasing or is it decreasing? Friend is moving away, wavelength is decreasing. And then frequency, it's definitely supposed to increase because they are inversely proportional. So our FL is increasing. No guys, no. Okay, so now remember guys, we need to check now what is happening to the frequency and what is happening to the wavelength. Starting with the wavelength, your friend is moving away from you, so the wavelength is increasing. Okay, I just need to use a different color. The wavelength is increasing, and then if the wavelength is increasing, frequency has to definitely decrease because they are inversely proportional. Now we write the whole formula, V plus or minus VL over V plus or minus Vs times Fs. Who is stationary? The listener is still stationary, so we have just V divided by V plus or minus Vs. And now what is happening? We are saying the frequency is decreasing. Our frequency is decreasing, meaning we expect this part to also decrease and that one to increase. We want the numerator to be smaller and the denominator to be bigger, meaning we want to add. Remember, if something has to be big, we add. That's how you can just grab it. If you want to make it big, you add. So it means we are going to work with a plus. V over V plus Vs times Fs. Now we can start substituting. Our V is still 340. I just need to also add that because I realized that I did not add it. Yeah, this is the velocity of the listener and the velocity of the source, and then the velocity of the sound, the speed of the sound is 340. Forgive me guys for keep on saying velocity. It should actually be speed. So 340 plus 10 times 820. So let us check it out. 340. And remember guys, when you plug this on your calculator, you can plug it like this. You can type this part in one bracket and then the other part in the other bracket. Please don't mistype it. You know, the most painful thing is when you know the method but you typed it incorrectly on your calculator and it ends up giving you a wrong answer. So our frequency of the listener is 796,57 hertz. So what are we saying now? We are saying the frequency was 820, and remember, going back to at the beginning when we started, we said if the source is moving away, what you hear as the listener should be smaller than what the source is emitting. Therefore, it means it is evident we got 796, which is, yes, smaller than 820. Okay, so guys, that's how you can use this whole method to decide on the direction, or to decide on your either positive or negative. I'm going to bring a past exam question that I want us to go through, and let us see if we can grasp some questions, and then we can now have a look at Doppler effect in terms of light. Okay, I hope you can see question 9.1. This was a question extracted from a past paper. One way to tell if a mosquito is about to bite is to listen to the Doppler effect of the sound emitted by the mosquito as it is flying. The buzzing of a mosquito's wings emits sound at a frequency of 1050 Hz. The speed of sound is 330 in air. So let us see what we've been given. They've given us the velocity of the source. The velocity of the source, they are saying it's no. So let us look at what they've given us. They've given us the frequency of the source. The source now is what? Is the mosquito. Is 1050 Hz. What else do we have? We have the speed of sound, just the V. It's going to be 330 meters per second. And what else do we have? We don't have much. That's just about all that we have. Okay, question 9.1.1, state the Doppler effect for sound in words for 2 marks. I know you guys already know it, and we know how to grab the 2 marks, not just 1 mark. The Doppler effect is the change in the frequency of the sound observed by a listener, because the sound source and the listener have different speeds of velocities relative to the medium in which the sound is propagated. That is Doppler effect. 9.1.2, if you hear a frequency of 1034 hertz, does this mean that the mosquito is coming in for a landing, or that it has just bitten you? Or has it just... Okay. Question 9.1.2, if you hear a frequency of 10,034, does this mean that the mosquito is coming in for a landing, or that it has just bitten you and it's flying away? Explain your answer. This question is 3 marks. So remember, we have the frequency of the source. We had said it's 1050 hertz. And now they say the frequency that you hear, the frequency of the listener, it's 1034. So guys, under which conditions do you have the frequency of the listener to be smaller than the frequency of the source? When the source is moving away from the listener, because when the source is moving away from the listener, the wavelength is increasing, the frequency of the listener is decreasing. So it means we will say 9.1.2, it is moving, it is flying away. It is flying away, and we need to give reasons. Firstly, frequency of the listener, it's smaller than frequency of the source, meaning wavelength. Okay guys, we need to write this in words, meaning the wavelength increases, causing frequency to decrease. Okay, that is it. We got the 3 marks. We even gave them an extra point. 9.1.3, calculate the speed of the mosquito when you hear the frequency of 1034. So you see now 9.1.2 is linked to 9.1.3, meaning if you missed the second question, your third question is going to be wrong. So first thing first, we write the equation V plus or minus VL over V plus or minus VS times Fs. Okay, so our velocity of the listener is 0, so now we are left with just V plus or minus Vs times Fs. So what is the story now? We are saying the mosquito is moving away. We had said on the second question that the mosquito is moving away, meaning wavelength is increasing and our frequency is decreasing, meaning this part over there is decreasing. It is directly proportional to the numerator. The numerator must be small and the denominator must be big. If we want the denominator to be big, we need to do what? We need to add. So we have V plus Vs, Fs, and Fl. The frequency of the listener, they had said it's 1034 if I'm not mistaken. Let's check. Yes. And then the velocity is 330 over 330 plus we are looking for the velocity of the source, the mosquito, times 1050. Okay, so now guys, we need to use our mathematical foundation. So 330 times 1050, it gives me 346,500. Divide by 330 plus Vs, and I'm going to multiply with the denominator. So I have 1034, 330 plus velocity of the speed of the source, it's equals to 346,500. Now divide both sides by 1034 and 1034. That cancels that. Now I have 330 plus velocity of the sound of the source, that divided by that, it gives me 335, I'm going to keep 4 decimal places. Guys, remember, when you are calculating, when you haven't gotten to your final answer, you don't have to round off immediately. You can still keep some decimal places, 3 or 4, then you can round off to 2 decimal places on your final answer, just for accuracy. Minus 330, that is going to be 5,1063, which is 5,11 meters per second. That is the speed of the source. Okay, so now that we have covered the Doppler effect under sound, the next thing that I want us to look at is the Doppler effect of light. So what we say, guys, is that in order for you to be able to see that there is a change in frequency or change in wavelength, that can be seen through, firstly, sound, which is the one that we have covered above, and then we can also see that through light, because sound and light both travel through the medium, or they both travel like in the space, in the air. So now when we look at the Doppler effect of light, we look at it in terms of what we call a redshift and a blue shift. So from redshift and blue shift, I'm going to say redshift means that the source is moving away from the observer. Source moving away. And blue shift means the source is moving towards the observer, or that observer or the listener. And then I'm going to explain what do I mean when I say red shift or blue shift. Okay, so I'm going to go back to grade 10, grade 11, when we did Roy G. Biv. Remember, guys, our R, okay, I just need to use a black pen. Our R O Y G B I V. Roy G. Biv, it's the electromagnetic spectrum. So R is for red, orange, yellow, green, blue, indigo, and violet. So Roy G. Biv tells us that when you move from the red towards the blue violet part, your frequency is increasing, meaning the frequency on red, it's going to be smaller, and the frequency on as you move towards violet, it's going to be higher. And when you move from violet to red, your wavelength is increasing, meaning the wavelength here is bigger and the wavelength there is smaller. Okay, so you need to know this with Roy G. Biv. When you move, it means red color has a smaller frequency and higher wavelength, or a longer wavelength, and when you go towards violet, violet has a higher frequency and a smaller wavelength. And then now when we say red shift, means the source is moving away. We are thinking about it in terms of, think about frequency of light, guys, or frequency of anything. When we did sound, we said when someone or when the source is moving away from you, the frequency is decreasing, right? The frequency is getting smaller. When someone is moving away from you, the sound that you hear is getting lower and lower and lower. It's the same thing with light. When light is moving away, it's getting dimmer and dimmer and dimmer and dimmer. So the frequency of light is decreasing. And then when something moves towards you, when the light source is moving towards you, it's getting, like, the frequency of the light is increasing. So that is why when we say redshift, we are saying if it's redshift, the source, it means the source is moving away. Why? Because frequency is getting smaller, it's decreasing. But if it's blue shift, it means the source is moving towards you. Why? Because frequency is increasing, and an increasing frequency means the source, it can be source of light, source of sound, it's towards you, but in this case it is going to be the source of light. So guys, with regard to the Doppler effect under light with the red shift and the blue shift, you just need to know that red shift means source is moving away, blue shift means source is moving towards you. If we make an example with because normally when we do Doppler effect under light, we talk about stars. We know that the universe is surrounded by stars. I'm not saying the universe looks like that, but I'm just using that just to show us a typical, just to say, okay, this represents our universe, and we have stars that are surrounding or flanking the universe, and the frequency that these stars are showing, or the frequency of the light from the stars to the universe will tell us if whether the star is moving either towards or away from the universe. Let's say I don't know how long it takes for a star to move, but let us say for an example, today, like at the moment, we use a certain device. I don't know what device we also use to measure the frequency of light. I don't know that deep about that, but let us say that device that we don't know measures the frequency from star 1. Let's say it's still okay, it's the same star. Let's say it's star 1 and the frequency from star 1 is 500 hertz. Okay, the frequency is 500 hertz. And then okay, we are done with star 1. Next week we now have star 1 again. We want to measure the frequency of that very same star. So when we measure the frequency of that so that was star 1, that very same star 1, the frequency is now 420 hertz. Okay, so the frequency was 500, is 500 today, but next week when we measure the frequency, it's 420 hertz. The frequency has decreased. What does that tell us about star 1? Is star 1 moving towards the universe or away from the universe? It means star 1 is moving away from the universe because its frequency is decreasing. It means star 1 is undergoing a red shift. So guys, this is all that we need to know about Doppler effect under light. You just need to know what blue shift is and red shift is. So if we are saying it's a red shift for star 1, it means it is moving away from the universe. So still looking at red shift and the fact that it is moving away, you just need to know that under this chapter your star is going to be your source of light. So the star represents the source because it's the one that is emitting the light, since we are doing Doppler effect under light. And then whatever that is, anything, it can be the universe or whatever they use, or any other planet, or any other planet would be the observer. So it means source is the one that is moving, the observer is stationary. Okay, so that's about all that we need to know about Doppler effect under light. Let us bring more questions where we have Doppler effect under light. We have to look at the application of Doppler effect. Where is Doppler effect being applied, or where can it be applied in real life? So I'm just gonna include that over there. Application of Doppler effect, application or applications of Doppler effect. So the first one, Doppler effect can be used in medicine, which is the most common asked question, and they can also further ask you how can it be used in medicine. So in medicine, Doppler effect can be used to measure the blood flow rate. It can be used to measure the blood flow rate. You don't need to know the details on how does it measure the blood flow rate. They won't test you on that, but you need to know that under medicine we can measure the blood flow rate. We can also do observation or observe the fetus heart rate. Fetus. How do we spell fetus? Fetus doesn't start with E, it starts with O. So it can also use it to measure the fetus or to observe the fetus heart rate. So this is being done during pregnancy. That is not rate. Also rate must have a T. Okay, so that is the application of Doppler effect under medicine. And then it can also be used in what we call maritime. So maritime is when they use the sonars. Maritime, so this is the sonar positioning underwater, but you don't really need to know how it works. You just need to know that we can use it in sonar positioning underwater. And then lastly, it can be also used by the law enforcement. And with the law enforcement, what it does is it can be used to monitor the speed of cars. You know, the monitor the speed of cars. You know, guys, speed trap, ne? They use Doppler effect. Okay, so these are the applications. Okay, let me just quickly, okay, let us now get into application of these questions. And one example that we can look at on answering questions under the red shift and blue shift. So the Doppler effect has many other uses. One of the uses of Doppler effect is in the field of astronomy. While studying the stars, a redshift emission is observed. Is the star moving away from the Earth or towards the Earth? So it means we have the Earth and we okay, that is a representation of our Earth, not exactly so earthly, and then we have the star there, and we want to know is the star moving away from the Earth or towards the Earth. So we know with redshift means we are moving towards the red part of Roy G. Biv, and if we are moving towards the red part, it means we are moving to lower frequency. So it means frequency is decreasing, and we had said that if frequency is decreasing, it means that the source of light is moving away. So our answer would be the star is moving away from the Earth. Okay, and then 9.2.2, another use of the Doppler effect is in the medical field. Give two uses of Doppler effect, of the Doppler flow meter on humans. So Doppler flow meter is a device that they use in medicine, and we have seen earlier on that the Doppler flow meter or Doppler effect under medicine, it can be used to measure the blood flow rate, and it can also be used to observe the fetus heart rate. Remember, guys, fetus, it's an unborn baby. So the fetus heart rate. So these are the two uses of Doppler effect, specifically where in the medical field. So guys, you must read these questions properly. If they say in the medical field, it means you are being specific. You are now going to just give the two under the medical field. Okay, so guys, this is the end of my video on Doppler effect. I hope everything that I have outlined made sense, and I hope you are going to approach Doppler effect with so much positivity, because after this video, guys, please make sure you understand. And tell you what, you can grab all of the marks under the Doppler effect chapter, because it's just a short chapter. You just need to make sure that you grab the application of the formula, how to change the pluses on the minuses, how to talk about red shift and blue shift. Thank you so much for watching, and guys, please do make sure that you are subscribed. If you are not yet subscribed, I'm always saying this, it's never too late, because there's more videos to come. I'm even planning on doing because we are approaching June mid exams, I'm going to do a past exam paper for physics and for mathematics, grade 10, grade 11, grade 12. So please guys, do subscribe so that you can get notified, so that we can make things easier for you to prepare for the final and also the June examination. Please also feel free to interact in the comment section. Tell me what you would like me to cover next on our next lesson. Believe me, that shall be covered. Thank you so much. Bye.